Dear student, warm welcome to NPTEL Phase 2 video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. This lecture number 35. Name of the course Geosynthetics Engineering in Theory and Practice. This module 6, lecture number 35, Geosynthetics for reinforced soil retaining wall. I will now show the recap of the previous lecture. We cover the gabion wall, general design of gravity gabion wall and design of gabion wall with welded or anchor mesh as a horizontal tie back, that partly cover. Now I will now continue with the remaining part of this example. So we have covered the external stability. Now I will address the internal stability, that is step 13. You have to calculate the spacing and the tensile force at each layer. The vertical pressure at any layer, if it is sigma z, will be equal to gamma s into z plus q, or q is the surcharge load, gamma s is the unit weight of the soil, and z at any depth of the layer from the top of the wall. Now tensile strength at any layer T calculated will be equal to sigma z into SV into K of A. So where Ka is coefficient of active earth pressure that we have calculated earlier, that is 0.27, and SV is the spacing between the two reinforcement. Now T ultimate we know it is about 60 kilonewton per meter. Let the factor of safety 1.85. So T allowable will be equal to 60 divided by 1.85 is 32.43 kilonewton per meter. Therefore, at the bottom, that is at z is equal to 10 meter, because this is the 10 meter height of the wall. So maximum spacing can be calculated as T allowable is equal to sigma z into SV into Ka. We know what is T allowable, we calculated 32.43, we already know this value, and then sigma z is equal to gamma s into z, and this plus this is the surcharge load Q into SV into Ka. So this gamma s is 13, z is at the base of the wall, that is 10 meter, and surcharge load Q is 39 into SV and Ka is 0.27. So from this equation you have to calculate that what will be the SV spacing between the two reinforcement. So SV can be calculated as 0.55 meter. Therefore, let us provide 0.5 meter spacing at few bottom layer and then the 1 meter spacing at some top layer. Calculate tensile strength T calculated at each layer. So you can see from the step 14 that you check the tensile strength at each layer. So, T calculated should be less than T allowable, that is 32.43 kilonewton per meter. In this table, you can see here, this is the 10 meter height of the wall, and up to this depth 4.5 meter, we are keeping the spacing between the two reinforcement 0.5 meter, and the remaining we are keeping 1 meter spacing. So, this gabion type of wall facing, it may be that 1 meter or it may be the 0.5 meter, half of the gabion as a facing in this zone. Now, sigma z we have calculated at different that depth. So, these are the value 57, and then it is gradually increasing, and then up to the 10 meter depth is 219 kilonewton per meter square. Now, you have calculated T calculated kilonewton per meter, it is starting from 15.31, and then you can see that it is increasing and 29.42. So, T calculated value is 29.42. So, this T calculated value, it should be less than T allowable value, that means 32.43 kilonewton per meter. If it is less than the allowable value 32.43, that means it is okay. So, that means T calculated less than 32.43 kilonewton, that is why it is okay. So, this design is okay. Sometimes when you will change this spacing between the reinforcement suddenly 0.5 to the 1 meter or like that, if you can do that, sometimes it may not be satisfied this T calculated value. So, you are to select the spacing also sometimes depending upon that what will be the strength of this material. So, you can go 1 meter, you can see which can be satisfy this criteria. Now, step 15, calculation of minimum embedment length, that is LEM. LEM is equal to 1.5 into T calculated divided by 2 into sigma z into C of I into tan of pi. Step 16, here to calculate the actual embedment length LE. So, at any layer at a depth of z, the actual length of the embedment past the wedge, that is LE is equal to L minus TG minus LA into HG minus Z divided by HG. We have already explained this embedment length. So, now LA will be also Hg into tan 45 degree minus pi by 2 minus Hg into tan alpha. So, this is L of E and this is L of A. Okay. So, that means that this part is the LE, that means which is the L, this is minus TG, and then this minus LA and into LA into H0 at any depth. So, that is why LA into Hg minus Z divided by Hg. Hg is the height of the wall and LA is this part LA. So, LA, this angle is 45 degree pi by 2. So, this angle will be 45 degree minus pi by 2. So, LA will be equal to Hg into tan 45 degree minus pi by 2 minus Hg of tan of alpha. So, you can calculate it from this. So, we can obtain that H of LA Hg is equal to 10 tan 45 degree pi 32 minus Hg 10 tan alpha value 6, so 4.492 meter. Step 17, check the embedment length. At any layer, this LE, that means actual embedment length, should be greater than this minimum embedment length. LEM is minimum embedment. Then if it can satisfy, then it is okay. So here detailed calculation have been shown. This is the depth Z. We know the spacing we have keep up to the 4. This is 1 meter spacing, and then after that remaining portion is 0.5 meter fitting. We calculated sigma of Z is 57.219 kilonewton per meter square. We calculated T, whatever the calculated is 15.31 kilonewton per meter to 29.42. Now we also calculated T calculated, which is less than 32.40 kilonewton, that means it is okay. Now the other part is that this is LE, this is LEM, and LEM always should be less than LE. So you can see that this is the L of E, embedment length, that is starting from 1.96 meter and then gradually increasing, it goes to about 6 meter. So this is the L of P, and if we calculate that L of EM, that is a minimum embedment length, it should be 0.462 going down to 0.23. So you can see this LEM value is always less than the LE, that means it is okay. So like that you can make the design. So this is the arrangement of the reinforcement in different layer, and we know this is the height of the reinforced soil wall, and this is the gabion as a spacing, gabion as a spacing. So here you can see that 0.5 millimeter spacing. So up to 13 layer you have given 0.5 millimeter spacing. That means 13 layer into 0.5 millimeter means you are giving up to this is 13 layer, and after that the remaining 3 layer at a spacing of 1 meter. So you are giving 1 meter interval, and this angle you know that alpha 60 degree, and this is given the TG, what you call 1 meter. This you know is minus TG, this is 1.05 meter, and this L is 4.95 meter. So you need also a proper connection with the gabion with this reinforcement, metallic reinforcement. It should proper strip is to be connected. So gabion wall generally the 1 meter cube. So in the bottom part you have to make half. That means 0.5 meter, then place the reinforcement, then 0.5 meter, then you place the reinforcement, like this up to that 13 layer, and after that this is 1 meter length. So like this you can also design the gabion wall. So this kind of the structure also has been implemented in India. So this is one that mechanically stabilized reinforced soil, this gabion retaining wall. This is courtesy to Dr. Asha. Now we will discuss the feasibility study on fly as a backfill material. This is a part of the work from our research scholar Ratan Lal, and most of the time that when we will use these fly ash for any reinforced soil retaining wall, the selection of the fly ash is very important. You cannot use that any fly ash as you like it. There may be the defined types of the fly ash is available, whether it is a bottom ash or from coal industry or from any other industry, steel industry. So you have to be careful that what kind of the fly ash material you should use as a backfill for the reinforced soil retaining wall. So, you have to find out exact the properties of the fly ash which will suit the criteria or specification for this retaining wall. So, that is why some feasibility study on the fly ash as a backfill material has been considered, and it found that this material may be the suitable, and then this material also has been used for the constructing of cellular reinforcement as a retaining wall. So, some experimental program have been performed in this institute, and this is a 4 parts. This is a direct shear test and one dimensional consolidation test, permeability test, and also pH value. So, experiment was conducted on the different moisture content, that is dry side of the optimum moisture content and wet side of the optimal moisture content. So, this figure shows the relationship between the moisture content and the dye unit weight. This is a compaction curve, and from the compaction curve we have determined what is maximum dye density is 12.1 kilonewton per meter cube, and optimum moisture content is about 24%. Now, we have selected the some moisture content on the dry side, you can see dry side moisture content. So, this is for 12% moisture content selected, then the 16% moisture content selected, then the 20% moisture content, when a dry side of the optimum moisture content selected 3. And similarly, this is the optimum moisture content. Similarly, wet side of the optimum moisture content also selected, that is 28 as well as 30 of 2. So, this the moisture content dry side and wet side of optimum has been selected for performing the test. Now, this side shows that variation of apparent cohesion on the fly ash with different moisture content. This x axis is the defined moisture content, and this is the apparent cohesion in kilopascal. So, you can see that apparent cohesion value is increasing with increasing the moisture content, and reach to the highest value, that means it may be 20.76 kilopascal. When it is reached to the 20.76 kilopascal at the optimum moisture content of the fly ash, and thereafter this apparent cohesion value are decreasing with increasing the moisture content. This cohesion of minimum value of 2 kilopascal was observed for Corradi fly ash when the compacted moisture content is 12% dye of optimum. So, when we take that 12% dye of optimum, and then you can find that cohesion value is minimum value, that is 2 kilopascal. So, this kind of result has been observed for Corradi fly ash when it is compacted with the optimum moisture content 12% of the dye of optimum. Now, this shows the relationship between the moisture content versus angle of internal friction. So, this is the variation of angle of internal friction of fly ash with different moisture content. You can note that there is no such variation is seen in the value of angle of internal friction of fly ash. So, you can see that this angle of internal fraction is reducing, but increasing the moisture content, but no significant development of the internal friction angle of the fly ash. So, only difference you can have that 5.4 degree, which is observed from the dye side to wet side of the optimum. So, angle of internal friction has the maximum value of 32.3 degree for the Karai D fly ash when the compacted moisture content is 12% dye of optimum. So, when 12% dye of optimum, you are having the good value of friction angle, that is 32.3, whereas you are having that cohesion value is very less. So, this is the combined experiment setup for one dimensional consolidation and falling head permeability test. So, you can also indirectly determine the coefficient of permeability from the consolidation test. So, this is the consolidation, that is the cell, and this is the connecting tube, and this is the burette here, and then this is the dial gauge. So, number of tests has been performed from the permeability and the consolidation test. So, this figure shows the variation of the average coefficient of permeability KAB with the different moisture content under different pressure. So, under different pressure starting from 10, 20, 30 kilopascal, 50 kilopascal, 100, 200, 400 and also 800 kilopascal. And see the relationship that average coefficient of permeability value. This value is decreasing, you can see here, with increasing this moisture content, and then here it is drop and then it is increasing. And you find that Karai fly ash have coefficient of permeability in the range of 1.42 into 10 to the power minus 7 meters per second to 6.31 10 to the power minus 8 meter per second. It is also observed by Tarjigi et al. 1996 that very fine sand and silt, mixture of sand and silt and clay, this coefficient of permeability value lies between 10 to the power minus 5 to 10 to the power minus 9 meter per second, as per Tarjigi et al. 1996. So, it satisfies this criteria. Here, this figure, this variation of coefficient of permeability with the vertical stress for different moisture content. So, here the dye side moisture content 12%, 20, this is 16%, then dye side of 20%, when OMC is 24%, wet side 28% and the weight is 32%. So, you can see that what is the variation of the average coefficient of permeability for the vertical, various vertical stress at different moisture content. So, next this is the E log of sigma p curve for fly ash for different moisture content. This x axis in log scale sigma p, this is the Bird ratio, you know that is consolidation test. This is under the different dye, it is 12%, 16% and 20%, and you know the OMC is about 24%. Then wet side we have selected 28% and the wet side we have selected 32%. So, you can see that nature of the relationship between the void ratio and also the sigma of V. And this the curve which is the variation of coefficient of consolidation Cb with the effective vertical stress, that is sigma V. This also the dye 12%, 16% and the 20%, you know OMC is 24% and the wet side also we have taken that 28% and 32%. You can see nature of the curve is the same. It is increasing, then little bit constant and then it is the increasing. That means this is coefficient of consolidation increasing with increasing the stress, vertical stress. So, here we can calculate that what will be the average value of compression index, which is called Cc. So, this compression index is 0.078, where sigma V is less than 100 kilopascal, and 0.092 when the sigma V is greater than 100 kilopascal. So, the average value of recompression Cr, that is 0.014. So, coefficient of consolidation also lies between 0.5 into 10 to the power minus 6 to 1.8 into 10 to the power minus 4 meter square per second. Also, we check the pH value, which is 8.12. This is lies in the range of pH value for reinforced backfill. So, we check the pH value also. So, this is the table given that different property. This is cohesion, angle of internal friction, coefficient of uniformity, that is Cu, plasticity index, pH value, organic content. So, here what is the result that obtained by Ratanlal Mandal 2012, that cohesion value you can see less 2 kilopascal. Angle of internal friction is 32.3 degree. Coefficient of uniformity it is 11.12. Plasticity index it is a non-plastic, and pH value 8.12 and organic content is 0.1035. So, now this value has been compared with the FHWA NH100024 or Berg et al. 2009. So, this cohesion value, this is cohesionless almost, cohesion value, angle of friction value greater than equal to 34, we are having about 32.3, coefficient of uniformity greater than equal to 4, here it is 11.12, plasticity index less than 6 is a non-plastic, and pH value, which is also important, it should be greater than 3 less than 9, our pH value greater than 5 or less than 3. In case of A, if it is a geosynthetics as a reinforcement, in case of B, what that steel reinforcement is used. So, we use this geosynthetics as a reinforcement, and which that value here we obtain pH is 8.12. So, it satisfies the criteria, and organic content in the fly ash is less than 1 and we have obtained 0.1035. So, it is 1. So, this kind of the fly ash you can say that satisfy the specification, and this low specific gravity, that is 2.15. So, less lateral pressure on the retaining wall, because fly ash is light material, with respect to what we use for the conventional specified backfill material. So, that was another reason that it is a good that it can reduce the lateral pressure on the retaining wall. The result of the permeability and consolidation test shows that the coefficient of permeability and the consolidation characteristics of the compacted fly ash were comparable to those non-plastic sealed and very fine sand. As you observe that what Darjigi has mentioned and what we obtained, so this is quite comparable. We find that coefficient of permeability is 1.42 into 10 to the power minus 7 meter per second. Angle of internal friction is 32.2 degree and apparent cohesion is 2 kilopascal and moisture content is 12% of dry side of optimum. So, you have to select that proper kind of the parameter. Now, compression index Cc is 0.078 when the sigma v value less than 100 kilopascal and 0.092 when sigma v is greater than 100 kilopascal. Fly ash can be used as a backfill material in reinforced retaining wall as the deformation due to loading will be less when it was properly compacted. The pH value is 8.12 is fall within the recommendation limit of electrochemical properties for reinforced field with steel and the geosynthetic reinforcement. So, it satisfies all the criteria. So, this is the how we talk about that how the fly ash can be used as a backfill material for the construction of the mechanically stabilized reinforced soil retaining wall. So, you must check the property of the fly ash whether it satisfies the specification or not. If it satisfies, then you can use it. So, what we find that the fly ash what we have been used and we perform the number of the tests, consolidation test, permeability test and the compaction curve and find that what moisture content is suitable for the compaction. So, this another greatest problem that moisture content, what moisture content, sometimes you can find that optimum moisture content may not be the suitable for the compaction in case of the fly ash. Most of the time in general we use the optimum moisture content for as a compaction and achieve to that degree of relative density, but it is not necessary in case of the fly ash. So, you have to be careful for selection of the moisture content in order that where cohesion value can be reduced and angle of friction value also can be increased and material can satisfy the all other criteria, pH, etc. So, this kind of the fly ash can be used for the mechanically stabilized reinforced soil wall. Now, also Ramnathullah have performed some test on the model test on geocell wall subjected to the strip loading. Now, geocell wall, it is like this you can say the geocell because we have cut from the waste bottle and we have prepared the geocell and it has a particular diameter and also the height. So, this we also call the geocell or the cellular reinforcement. So, you can construct this in the form of the mat and then it can be jointed, okay, and we find that this kind of jointed is suitable there is no problem, and then you can fill up with the filling material into the cell and you can compact it. So, this is one that in the mat form you can use it. Also you can use this geocell in the strip form. So, you can give the spacing and then you can put the another of the strip geocell, and this geocell also you can fill up with the pliers and can be compacted. So, this kind of the system is adopted in this experimental program. This is a kind of new innovative system where it has been performed in this lab, and here part of this experimental work is presenting, that is on model test on geocell wall subjected to strip loading. So, experimental program geocell wall, there are 12 model. So, this is GTW indicate gravity type of wall. When the facing angle 90 degree and reinforcement side CRW means cellular reinforced wall. Then this gravity type wall also the angle change 80 degree, 70 degree, but all cases we use the cellular reinforced wall. And the model number 4 FTW, that is facing type wall. So, from model 4 to 11 we have used the facing type of wall, but angle also change, it may be 80, 70, 90, etc. And also the some cases we have used that cellular type of the reinforced wall, or some cases that cellular reinforced wall plus top layer, cellular reinforced layer plus bottom layer, cellular reinforced layer total layer. What I want to mean is that sometimes that if this is the facing, this is the cellular reinforcement, so you can construct the gravity wall only with this cellular kind of reinforcement. You can place like a gabion, you can place one, then you can place another one here, then you can place another one here. So, then you can construct a gravity type of the wall. So, that is gravity type of the wall. Also you can place this, only this or like this part. So, this will act as a facing element. So, this is facing type of wall, facing element, and then you can add the reinforcement also. It can be connected reinforcement also, like this it can be connected, and that also that you can sometimes use this as a reinforcement, cellular as a reinforcement. Facing element you can use this cellular as a reinforcement at a particular facing. Okay. So, you can use this kind of cellular reinforcement as a gravity retaining wall, or you can use as a facing element, and also the cellular reinforcement you can use as a strip. So, these are the model defined and experimental work have been carried out. You can see that different types of the geometry of the model has been considered. So, this is, let us say, model 1, and I mentioned that what is GTW, that is gravity type wall. So, this is gravity type wall. You can see that cell, and this theta angle is 90 degree, this is gravity type. This is one model. This is 2 cell whose length is 140, and here is the 1, 2, 3 cell whose length is 210, and each cell is 70, and this theta 90 degree. Then you are applying the strip load here. Then this is another type. Here is a batter is 10 is given, and this is height of the wall 350, and here theta 80, here 2 cell L is 140, here 3 cell or L is 210. So similarly, here theta 70 degree, angle is changing, here 2 cell, here again the 3 cell, here better angle change to 20 degree. Then this model wall 10, this is as a that FTW, FTW means facing type wall. So this is facing type wall. So only facing, you can see this as a facing, 1, 2, 1, 2, this is cell as a facing, and this is the reinforcement, this is the reinforcement. Here is the reinforcement 210, and this is only 2 cell as a facing element. Similarly, this as a model wall 11, this act as a facing element, and this as a length of the reinforcement. And then you are changing the length of this, I put at the top, this is placed at the bottom, and this you place, then theta is equal to 90 degree, is all case theta 90 degree, and you are place the number of the layer of the cellular reinforcement, and this cellular act as a facing element, and then you are applying the steep loading in all cases. So different types of the model have been selected and optimized. So this is the that what you call that photograph of geocell, which is made up of the plastic waste bottle, and fly ash has been used as a backfill material. What we have discussed earlier about the fly ash, the same fly ash has been used as a backfill material, which is locally available. This plastic bottle have used to prepare the geocell, and this diameter and the height of the unit geocell was 70 millimeter. Now, what you know the why we are also interested to study, you can see lot of the plastic bottle, it is very difficult to control. And here you see that plastic waste quantification in 4 metro cities of India. CPCB 2012 reported that city in Calcutta, it is total plastic waste generated about 425.35, and plastic waste collected from the recycling the 255.21 tons per day. Uncontrolled plastic waste about 170.14 ton per day. Similarly, Chennai 429.30 ton per day, this is total plastic generated. 257.58 is the plastic waste collected from the recycling, and 171.72 uncollected plastic waste, this ton per day. Mumbai 421.01 total plastic waste generated, and 252.60 plastic waste collected from recycling, and 168.40 uncollected plastic waste. And Delhi 688.84 total plastic waste generated, and 413.30 ton per day plastic waste collected for recycling, and 275.536 uncontrolled plastic waste ton per day. So if look that what will be the kind of the plastic waste is uncontrolled. So it is almost that 40%. So we can make use of this kind of the plastic waste bottle for the construction of the reinforced soil retaining wall, and also it can be used for the road construction. So number of the tests has been conducted. Here you can see that what will be the lateral deformation of the wall. So this curve shows with the relationship YH by H, H is the height of the wall, and this is delta H by H in percentage. This is under the different load. This is 22.65 to 47.55. This is model number 1, theta 90 degree. So, effect of the facing angle. So, delta H by H value increase with increasing in surcharge pressure until failure occur. Even delta H by H value increase with increasing the delta H by H value, indicating that maximum lateral deformation delta V maximum of the wall occur the crest portion. The failure surcharge pressure QF are increased with decreasing the facing angle. Similar result was observed for the facing type of wall. Now, here also that YH by H to delta H by H in percentage, the relationship for the top layer of the reinforcement model 10 and bottom layer of reinforcement 11 under this is load. So, from the bottom layer of the reinforcement backfill geocell wall, the delta H by H value increase with increasing YH by H value, indicating that the maximum lateral deformation of the wall occur at the crest portion. Whereas, for top layer of the reinforced backfill, the geocell wall, the maximum lateral deformation occur near about the mid height of the wall. You can see sometimes mid height of the wall how it is occurring. Now, settlement of the backfill. This is the relationship between the QY delta H versus this is P by B, this is percentage, this is for model number 1, 2 and 3, theta is 90 degree, 80 degree and 70 degree. This is a gravity type wall. So, you can see the relationship here. So, similarly, this one also facing type wall. So, this is gravity type wall, this is facing type wall and this is Q by gamma H, x axis and P by B, this is percentage. This is for model number 4, model number 5, model number 6 and theta is 90 degree, 80 degree and 70 degree. So, you can see that nature of the curve is the same. So, relationship between the backfill settlement and the surcharge pressure shows non-linear for all facing angle, whether it is 70, 80 or 90 degree, it is all non-linear. The backfill settlement are increased with increasing the facing angle. So, result and the discussion. So, here we have shown that model number 1 to 12, this facing angle degree 90, 80, 70, 90, 80, 70, 90, 80, 70, 90, 90, 90. Here this star, you can see here this star 1 and 2 and 3, which is gravity type wall. So, this is all gravity type wall. What the facing angle is 90 degree, 80 degree and 70 degree, and you are having Q A by gamma H value 12.51, 14.11, 14.68 and delta H maximum by H percentage 0.525, 0.557 and 0.576 and rho max by B percentage 6.390, 6.696 and 7.196. Now, in case of model number 4, 5, 6, 7, 8 and 9, this star indicate facing type of wall. So, these are the facing type of wall, which facing angle also change 90, 80, 70, 90, 80 and these are the QA by gamma H value and these are the delta max by H percentage value. So, rho max by B value you can see here. Similarly, for 10, 11 and 12, that is facing type wall, that is backfill reinforcement. So, that means facing and the reinforcement is provided. This is facing angle 90, 90 and 90. So, we are having that QF by delta is 16.27, 15.33, 18.35 and this delta is maximum value 0.315, 0.353 and 0.308 and rho max by B percentage 7.991, 7.952, 9.312. So, you can see that different types of the model, different types of the facing angle and it is gravity wall and only facing type of wall and facing type with the backfill. So, lateral deformation it can be observed that is reduced by 30 to 40% in case of the reinforced backfill compared to the unreinforced backfill soil. So, how the lateral deformation has drastically reduced. So, what are the major findings from this experiment? The normalized lateral deformation of the wall delta H by H increase with increasing the surface pressure Q until the failure occurs. Delta H by H increase with increasing the normalized height of the wall YH by H indicating that maximum lateral deformation of the wall occur at the crest portion that is delta by H decrease with decreasing the facing angle of the wall. Now, for the top and total layer of reinforced backfill model, the maximum lateral deformation occur at about mid height of the wall. The failure surface pressure QF are increased with decreasing the facing angle. Reinforcement in the backfill reduce the lateral deformation of the geocell wall. The reduction in normalized maximum lateral deformation delta H max by H percentage of the geocell wall was about 30 to 40% with respect to unreinforced backfill. The relationship between the normalized surface pressure Q by gamma H and normalized settlement of the backfill rho by B was observed to be nonlinear for all the facing angle. Settlement of the backfill was increased with decreasing the facing of the wall. You can see here also that cellular type of the reinforcement and has been used. This is the cell type of reinforcement and filled up with the compacted backfill material. So, this type of the wall also can be constructed and also you can put the green color. So, it looks like a greenery. Also sometimes you can make a hole on the cellular reinforcement and the grass also can grow. So, you can make a greenery reinforced soil retaining structure. So, behavior of cellular reinforced fly ash wall under steep loading. Steep load applied to the top of the backfill through a loading plate having the dimension thickness 10 millimeter, width 100 millimeter, length 350 millimeter and position 150 millimeter from the facing panel. Here CD10 is the cellular reinforced of diameter 50 millimeter and height 10 millimeter. So, these are the different types of the model 1, 2, 3, 4, 5 with the different aspect ratio. This is H by D. So, this is aspect ratio H by D 0.2, 0.4 and this is the vertical spacing 0.22 H and this is the different length has been considered. What here that C and D15 indicate that D is the diameter, that is D50 diameter and this is the height H of the cellular reinforcement and number of the experiment also has been performed. So, this is the H is the height of the facing panel 500 millimeter and this is the cellular reinforcement diameter also varying and height also varying. So, this is the aspect ratio. So, these are the experimental program has been performed and this is the fly ash model. This is the line sketch has been shown how the steep load has been applied and here is the LPTD. So, this is the cellular reinforced used in the model. Experiment was made up, locally available, that plastic waste bottle, and I say that C5010 mean this is the diameter, this is the height, this is the diameter of the plastic bottle, and this is the height 20, this is the diameter 70, this is 15, C70 30, then this is diameter and this is the height. So, this different types of the placement, and it has been placed in the matrices form. It has been placed also in a RC value, RCI manner, coverage ratio. This is 0.5 and this is 0.6. This placement of cellular reinforcement strip, it is in the form of strip also has been used. So, this is the failure surcharge pressure and the lateral deformation of the facing panel. So, cellular reinforcement in the form of the matrices, unreinforced case Q by gamma H is 2.84. Effect of length of spacing cellular reinforcement C 50 and 10. So, you can see defined value of LR by H, the length of the reinforcement by height of the wall, and SR by H 0.22, 0.32 and 0.32. So, you will have that QL by gamma H value for the SR by H is equal to 0.2, SR by H 0.30, you can have QR by gamma H and delta max by H value, and SR by H 0.42, you can have QA by gamma H value and SM by H value. So, you can see that how the difference in the value of, because for defined value of SR by H and length by H. So, what we can say that increasing LR by H ratio corresponding the higher value of surcharge pressure, increasing SR by H ratio corresponding to the lesser failure of surcharge pressure, increasing the height of the cellular reinforcement height H correspond to the higher value failure surcharge pressure, indicating the better performance of the wall in terms of carrying the load before failure. So, this is the cellular reinforcement in the form of strip. So, where you can see RC value, that cellular reinforcement 6 for C5010 use, for RC value 0.5, 0.6, and for cellular reinforcement C5020, diameter same but height is different. So, RC value 0.5 and 0.6. So, for the defined value of L by RH value, so you are obtaining the defined value. So, here you can see that when RC value 0.5 is 7.73, when RC value is 0.6, this value is 8.89, that means it is increasing. This value you can see when the cellular reinforcement, when the diameter is 50 but height is 50, RC is 0.5, this is 8.75, but when the RC is 0.6, then you can see that 10.47. So, it is observed that when RC is 0.6, this value is increasing, when RC is 0.6, this value is increasing. So, this may be the most suitable, and what we have also performed this kind of the coverage ratio in case of the geogrid material. So, these are the some result you can see under the defined load, defined height, and you can see that how this is increasing this value like this. So, what is that the variation of between the Y by H and delta by H was found to be almost linear for all surcharge pressure. The delta by H value increase with increasing in surcharge pressure until the failure occur. The delta by H value increase with increasing the Y by H value, indicating that the delta maximum occur at the crest portion of the facing panel. For a particular value of surcharge pressure Q, increase the height of the cellular reinforcement H, so less facing panel displacement. So, this is the for the mattress case, you can see delta H by LR by H value, and it is decreasing at almost the constant. Also for strip case, it gives the same nature of the curve. So, for backfill settlement, relationship between normalized surcharge pressure Q by gamma H and the normalized settlement of the backfill rho by B were plotted. So, here key variable rho is the settlement of the backfill material and B is the width of the loading place, that is 100 millimeter. So, this is the cellular reinforcement form of matrices, effect of length with the cellular reinforcement C5010. So, this relationship between the Q by gamma H and rho by B with different L by R ratio. You can see that then what conclusion we can draw. Most important factor which govern the behavior of the cellular reinforced fly ash wall are found to be failures such as pressure, horizontal displacement of the facing panel and backfill settlement. These factors are significantly influenced by the parameter like length of the cellular reinforcement to height of the facing panel ratio LR/H, vertical spacing of the cellular reinforcement to the height of the facing panel ratio, that is SR/H, and dimension of cellular reinforcement, that means diameter and height, and the reinforcement coverage ratio. The increasing the height of the coverage ratio of cellular reinforcement corresponding to higher value of failure such as pressure QF, indicating better performance of the wall in terms of the carrying load before failure. Also, failures such as pressure are increased with increasing the LR/H ratio and decreasing the SR/H ratio. The model testing findings suggest that it may be possible to use LR/H ratio less than typical value of 0.7 when the backfill is reinforced with cellular reinforcement in reinforced wall. However, more studies must be carried out before it can be used in the actual project. The normalized displacement of the facing panel delta/H increase with increasing normalized height of the facing panel Y/H value, indicating that maximum horizontal displacement of the facing panel occur at the crest portion of the facing panel. The variation between Y/H corresponding to delta/H was found to be linear for all surface pressure. The relationship between the backfill settlement and the surface pressure is found to be nonlinear for all the model wall. The settlement value at failure condition increase with increasing the LR/H ratio and dimension of the cellular reinforcement. You can see some kind of the application of the geo wave, where here is the building, where the geocell has been used, and then the grass can grow. Here also in the canal where the geocell also has been used. Please let us hear from you any question. Thanks for listening.